This is level 1 of the CFA program, the topic on quantitative methods and the reading on organizing, visualizing, and describing data. This is part 2, a logical extension of part 1. Let me just remind you that we talked about the importance of collecting data and organizing data and maybe coming up with some characteristics of that data. And remember that I said to you that the CFA Institute wants all of us as good financial analysts to be able to identify data sets and then do something with those data sets. And that do something is to make decisions. And so that's pretty much what we're going to do here in part 2. We're going to call this measures of central tendency. And please just think of central tendency, as I always do, as the point in the middle. But the second component of that thought is that we have these observations around the point in the middle, and the dispersion of those observations is going to tell us a lot about that data set. So if we look at the learning outcome statements, notice that we have a handful of calculate action words, so that'll be super fun. But that first one is super important. Calculate and interpret measures of central tendency. If we can focus on that one, then the other LOSs pretty much fall into line. We'll have an interesting conversation at the end of our slide deck on skewness and kurtosis, and then we'll hit another important LOS, describe and interpret covariance and correlation between two variables. So let's start with that first one, which I think is very important. Measures of central tendency. So this is the point in the middle, but there are a handful of ways of arriving at that point in the middle. The mean, the median, and the mode. Let's go ahead and start with the mean. And we need to make sure that we distinguish between a population mean, which is a representation of an entire population of a variable, versus the sample mean, in which we just kind of reach into a population and grab certain points. And I'm guessing that you remember how to compute the mean all the way back when you were 10 or 12 years old. You simply just sum all the observations and then divide by n, although we'll have some adjustments to be made here as we move through the slide deck. I want to call your attention to the last arrow point down there. The reading makes an interesting statement about the arithmetic mean being an excellent measure of performance in a forward-looking context. And I have a couple of thoughts about that, but clearly what the reading is trying to convince you is of the following. Let's suppose that you have a data set that includes the last 5 years of returns for a particular mutual fund, and you want to try to predict the future. Well, the most logical starting point is to look at the mean or the average return over that last 5 years and suggest that that's the most likely outcome over the next 5 years. And if you believe in that, what you're tending to believe is that history does repeat itself. And that's true for many variables, but it's not true for all variables in all cases. And I'll show you an example of that here in just a little bit. The weighted mean is going to be important, especially in the context of portfolio construction. Let's take a really easy example here. Let's suppose you have a portfolio that has 3 assets in it, and those 3 assets are expected to return 10%, 20%, and 30% individually. Well, if you take the arithmetic mean, here, let me just swing back here quickly. If you take that arithmetic mean, you're going to get 20%, right? 10 plus 20 plus 30 divided by 3, that's going to give you 20%. However, let's suppose in that portfolio construction that 80% of your wealth is invested in that asset number 1 and only 10% in each of asset 2 and 3. Well, then 20% is probably going to overstate it. So weighted mean is going to be important for portfolio construction. We'll call it the weighted average or the weighted portfolio return. Geometric mean is an interesting kind of a concept. What it does is, instead of adding all of the individual observations and dividing by n to get the arithmetic mean, it multiplies. So notice in the geometric mean equation, we have a multiply sign in between x1 and x2 and x3 and so forth. Well, in order to get the mean, we're not going to multiply and then divide by just n, but we're going to raise it to the 1 over the nth power. Notice that second diamond point. The formula only works when we have non-negative values. And so we could apply this to a sports analogy. I love giving sports analogies. Let's suppose that over the last 4 basketball games, LeBron James has shot 6, 8, 10, and 12 foul shots. And we want to try to make a prediction over how many foul shots he's going to shoot in an upcoming game. Well, clearly, if we do the regular old arithmetic mean, what did I say? 6, 8, 10, and 12. Well, that mean is going to be 9, right? But if we do the geometric mean and we multiply those 6, 8, 10, and 12 and then raise it to the 1 over 4th power, we're going to get something less than 9. Maybe it's 8.7 or 8.8. But the cool thing about the geometric mean is that it includes the nature of compounding inside of those variables, which lends itself perfectly to an analysis of portfolio or individual asset returns. The geometric mean is probably fairly useless when trying to predict LeBron James's foul shots. But if we have a portfolio of returns over the last, let's say, 5 years, 2%, 8%, 12%, minus 6%, and 14%, we can compute a geometric mean, and that's going to be an excellent measure of past performance. So I want to make sure that I call your attention to this. Look down here at the very bottom arrow point. Forward-looking contest for population and sample mean, past performance for geometric mean. That sounds an awful lot to me like an obvious question to ask on the exam. But I want to give you just a quick example here. Bear with me for a minute or two. Let's suppose that I'm your money manager and you send me $100, all right? And I do all sorts of stuff with your $100. And at the end of that first year, I've turned that into $200. That's a 100% return. And then during the second year, I do a whole bunch of stuff with your $200 and I turn it back into $100. So you handed me $100. 2 years later, I hand you back $100. Now let's see the difference between the arithmetic mean and the geometric mean. And by the way, this is a standard example that's in thousands of textbooks and thousands of professional presentations throughout the world. But I'm going to come to you as your money manager and I'm going to say, hey, I deserve a bonus. Watch this. The average of 100% in year 1, and then we lost 50% in year 2, right, from 200 down to 100. Well, 100 minus 50, that's 50% divided by 2. I averaged a 25% return, and I'm going to look at you and say, hey, I deserve a bonus. And you're going to scratch your head, and you're going to say, wait a minute, Jim, I started with 100 and I ended up with 100. How can I pay you a bonus? And you're going to whip out your CFA geometric mean book and you're going to say, wait a minute, let's compute the geometric mean. Let's take 1 plus that 100%. That gives me 2. Let's take 1 minus that 50%. That gives me 0.5. If I say 2 times 0.5, that gives me 1. If I raise that to the 1/2, that gets me 1. Then when I subtract out 1, that gets me 0%. So you wave that book in my face and say, wait a minute, Jim, the geometric return was 0%. You're going to say, dude, I'm not giving you a bonus. You're fired. Harmonic mean is going to be really important when we have a conversation on ratios. This is going to really hit us in level 2 when we do something like the price earnings ratio or maybe the cash flow to earnings ratio. So look at that diamond point. It's used to determine average growth rates of economies or assets. And so this is a really interesting calculation where you put n in the numerator and then you sum the reciprocal of all of those observations. And I'll show you a quick example here in just a few seconds. Trimmed mean, a measure of central tendency in which it is calculating excluding a small percentage of the lowest and the highest values. For example, if we're trying to compute the point of central tendency for touchdown passes thrown by Patrick Mahomes on any given Sunday. Sometimes it's 0, sometimes it's 5, sometimes it's 3. What could we do? We could exclude a small percentage of, the 0s and the 5s, or this Windsorized mean. What we could say is something like, oh, if Patrick throws 0 or 1 touchdown passes, we'll just say that's 1. If he throws 5 or 6 or 7, we'll just say that's 5. So go ahead and read those definitions for the trimmed mean and the Windsorized mean, and think about what's happening here in the two extremes. What we're trying to do with trimmed and Windsorized mean is to lower the influence of those outliers. Calculate and interpret. So that'll help you answer that question on trimmed and Windsorized mean. Median, of course, you learn about the median when you learn how to drive. My father used to always say, it's better to be on the right hand. Now this, of course, driving in the United States, it's better to be over here closer to the line on the right than closer to the line on the left, which is the median. Stay away from the median, because if you crash into a car coming to you, it has more of a violent reaction than if you just crash into a parked car over here. So one interesting kind of a footnote here to this concept of the point of central tendency as the median is that in the academic world, you hear this all the time about faculty salaries. Well, the mean can be a little bit inflated, especially if you're comparing it against schools where professors make tons and tons of money. So it's a fairly common standard to look at the median faculty salary. And so look at that second diamond point. Yeah, the median is resistant to the effects of extreme observations. The mode, of course, is the one that occurs most frequently. Some data sets have a mode and some don't have any. So how about if we take a look at some stock returns over the past 6 years? 2%, 2%, 4, 6, 8, and 12%. Let's go ahead and compute all of these points of central tendency. And feel free to pause the recording and get out your calculator to make sure that you can confirm that all of these are accurate and that you can calculate this on the exam, because the LOS does read calculate. Notice the arithmetic and the weighted mean are identical because the weights are equally distributed. Once again, there's the geometric mean where we add 1 to each of the decimal forms of those interest rates and then raise it to the 1/6 power. Notice that the geometric mean, 5.61, is going to be less than the arithmetic mean. That's going to be the case. Notice that the harmonic mean has 6 in the numerator. The mode is 2% because that's the most commonly observed data point. And then the median is just going to be the two midpoints, 4 and 6 divided by 2. That gets you 5. Here's a good slide to memorize types of data going down the left-hand side, and then when is their most likely or most useful type of point of central tendency. I think we covered all those points. Yep. How about quantiles and interpret related visualizations? We can divide things into 4. That's a quartile. We can divide things into 5. We can divide things into 10. I mean, we could divide things into almost anything, right? But I'm guessing that we picked those numbers because they are divided equally into 100, and that gets us down to percentiles. Split the data into 100 equal parts. My children will tell you that we live in our family here in a world of percentiles. Whenever my children are sick or whether they're hurt, I ask them what their percentile is. And of course, I always get a low-balled answer. Oh, I'm sick. I'm 5%, Dad. I'm 5%. I need to stay in bed and sleep. Yeah, let's look at that box and whisker plot. And this is really a super related visualization to give us a sense of the data set. So let's just go ahead and start at the top and the bottom. So there's the maximum and the minimum. And then we can throw our points of central tendency in the middle, right? There's the mean and there's the median. And then we also, in this box and whisker plot, are going to put the first and the third quartiles. And so all we're going to do is compute that interquartile range that's shown to you up at that slanted arrow point, Q3 minus Q1. Range is simply maximum minus the minimum. That's an obvious notion there. Mean absolute deviation. So here's where we start our conversation that I hinted at the beginning of the slide deck. So remember I said point of central tendency is just some point in the middle, and I've shown you a variety of ways to compute or estimate that point in the middle. Now we want to know what is the dispersion around that point in the middle. And think about it this way. If the total dispersion around that point in the middle is just about this much, well, what we can say is that we have a lot of confidence in our point of central tendency. But can you guys see this? If I go out of the screen, if our measure of dispersion is that high, then we have less confidence. So think about that measure of confidence about our point of central tendency as a measure of risk. Oh man, this is going to be so important as we go through quantitative analysis. So the first point here to make is to consider this mean absolute deviation. And all we're going to do is compute the mean, right? There's the arithmetic mean. That's X bar over there to the right of the minus sign. And we're going to subtract from that, we're going to subtract that from each value inside of the data set, but it's important to remember we're going to subtract each absolute value of each item inside of that data set. Now here's where we get really interesting and really into the meat of the beginning of statistics. Variances. What we're going to do is we can compute a population variance if the data set is from the population, or we can compute the sample variance if we have reached into a population and extracted a sample data set. And so both of these are computed in the same manner. Notice the population variance, which is noted by the Greek letter lowercase sigma, and it's a squared value. Always remember that a variance is a squared value. And what we're going to do, remember back here in the mean absolute deviation, we took the absolute value of each observation and subtracted it from the mean value. Well, in variance, we're not going to worry about absolute values. We're going to take that actual value, whether it's positive or negative, and subtract that from the mean. And then we're going to square it so that we get rid of the negative to be able to make sure that we consider all of the distance between each observation and the mean, and that those distances don't cancel each other out. That's why we square it. Now, you should be noticing that the population variance and the sample variance, they pretty much look like the same equation, and in fact they are. However, in the population standard deviation, what we're going to do is we are going to divide by n. In the sample standard deviation and variance, we're going to divide by n minus 1. Those are known as degrees of freedom. And I'll give you a good sense of degrees of freedom in the next handful of readings. So remember, divide by n for population variance, divide by n minus 1 for the sample variance, and then you take the square root of those two to get the population standard deviation and the sample standard deviation. So let's go ahead and compute a handful of these things. We have the returns on 6 different large cap stocks over 2021. So we have the population data. We've identified that as the year 2021, 6, 7, 12, 2, 3, and 11. So here's our arithmetic mean Just sum those and divide by 6. There's the mean absolute deviation. Take that 6% first observation minus the mean, 683. Notice we have the mean bolded in red. And then sum those, divide by 6, and you get a mean absolute deviation of 3.17%. So there's our first sense of a measure of dispersion. So what's that point in the middle? We computed that point in the middle. It's around 7%, but that mean absolute deviation is going to be 3.17%, the mean deviation above and below. That means that we don't have 100% confidence that our arithmetic mean is exactly going to be able to describe the entire data set. And of course, what we can do then is we can compute the population variance. There's the sigma squared. And notice that we do the same things, but we're squaring that difference. And then we're going to divide by 6, take the square root of that, we get 3.72%. Now, as we move through these early quantitative methods readings, we're going to learn more about the application of standard deviation and mean absolute deviation. But what I want you to do for right now is think about it in the following manner. Remember, I said a few moments ago that it is a real helpful measure of risk. Well, I want to take it an even more general idea here and make this interpretation, right? The LOS, calculate and interpret. So we believe that the middle value here is 6.83%. We've calculated the MAD, we've calculated the population standard deviation, and they're, 3%, 3.7%. This is a measure of how wrong you can be relying on that measure of central tendency. And this should make perfect sense. If the mean absolute deviation and the standard deviation for some reason turns out to be 0%, then you have 100% confidence in that estimate of the point of central tendency. If it's positive, well, if it's positive and low, then you have lots of confidence. If it's positive and high, then you have no confidence. A measure of risk or uncertainty. And here's a good note. If we were working with a sample, we would have divided by 5. Here, let me go back here. Divided by 5 in that population standard deviation. We divided by 6 because it was the population. If somehow we were given in the question stem that this was a sample, then we would have divided by 5. All right, how about target downside deviations? All right, so semi-variance and semi-deviation, they are average squared deviations below the mean. And so I want you to think about this. The semi-deviation and the target semi-deviation, these are measures for pessimists. And as good financial analysts, we need to be pessimists. We need to say something like, all right, what's the worst thing that can happen? If things go well, like if we're a portfolio manager and the economy is expanding and we're generating returns of 12% and 17% and 19% and 22% and we're beating our benchmark every year, then we're high-fiving and everyone's happy. But of course, we need to be prepared for that downside deviation. How about if I call it downside risk? We need to say something like, all right, if things don't go our way, if the worst happens, then what is the outcome or the expected outcome? And then let's spend some time now preparing for that downside risk. And so there's a good equation for the target semi-deviation where we have some acceptable level of risk or some acceptable deviation from each observation. Let's go ahead and do a quick example. Target downside deviation if the target return is 20%. So there we have a bunch of returns. And let's go ahead and put this in a matrix. I think this is probably the easiest way to do this. So there are the returns once again. The deviation from the target, so our target is 20, but the return was 36. So that deviation is 20%. And it was above, so we just ignore it, right? So all we're going to do is focus on those deviations that are below the target. That's that, the fourth column there, deviation below the target. And then we're going to square them just like we did before, add those together, divide by the degrees of freedom, and get target semi-deviation of 17.21%. Let me just remind you, raising something to the 0.5 is the very cool way of taking the square root. How about coefficient of variation, CV? This is a measure of the spread that is a ratio of what we just computed versus what we had computed earlier on in the slide deck. So for a sample, we have the sample standard deviation over the sample mean. For a population, we have the population standard deviation over the population mean. So think about this. In the numerator, there's a measure of uncertainty, a degree of error, right? And in the denominator, there's a measure of that point of central tendency. Let's go ahead and calculate that with 5 observations. And so feel free to pause the recording here and confirm that 40 and confirm that 5.5227. And by the way, the reading takes the candidates through a number of examples throughout this reading in which they show you the steps, 40 minus 40 squared, 45 minus 40 squared, and go through a table. Now, I'm guessing that there are many of you who are saying, oh, wait a minute, Jim, show me how to do this in your calculator. And I promise that we will go ahead and show you the calculator steps when we get to maybe some more intricate examples. But for now, for those of you that have this calculator, and let me just remind you, this is my favorite calculator. Let me take my glasses off so I can see. You have a sigma plus button right down here. So just enter all the observations followed by the sigma plus button. And then right underneath the 0 is an S, and right underneath the decimal point the 0 is the X bar, and right under the decimal point is the S. So you can compute those two means and standard deviations. That way, if you have this calculator, note you have look under the 7 and the 8, you have a data and a stat function. Just hit the second data and then second stat, and that'll help you get started if you want to do a little bit of research on yourself on how to use that calculator. But again, we'll go ahead and do that for you in an upcoming recording. And then when you have those two outputs, then just divide them and you get a coefficient of variation of 13.8%. Now, what we like to rely on as good financial analysts is this concept of a normal distribution, which is right in the middle, where the mean and the median and the mode are the same number. Now, let me go ahead and warn you, we're going to talk at length about normal distributions here in upcoming readings. But for now, notice that the reading tells you that this is a symmetrical distribution, which means that the stuff that's on the right and the stuff that's on the left are just mirror images of each other. And of course, the delineation between right and left is the mean, the median, and the mode. Now, what we say about this normal distribution is that the data set can be described by the first 2 moments of the distribution. Mean is the first moment, standard deviation is the second moment. And there are no third and fourth moments. But let's go ahead and look at this LOS. It should read something like this. Hey, candidates, skewness is the third moment of the distribution, and let's figure out what it means. So here are some standard ways to memorize this. Look at those arrow points. If the mean exceeds the mode, then skewness is positive. If the mean is less than the mode, then skewness is negative. And there's some examples there. And there are tons of examples out there that you can find about which data sets are more or less likely to have positive or negative skewness. And then down at the bottom illustration, we have some good pictures. And so the easiest way to remember this is that if you are skiing down the gentle slope to the right, that's positive skewness. If you're skiing down the gentle slope to the left, that's negative skewness. There's one of those quick ways to memorize things without really having to know anything about distributions and skewnesses. Skewnesses or skewni, what is the plural? Now, also note that the LOS does not ask us to compute skewness. However, the formula is in the reading, and so we thought we would put it here so that you get a sense of exactly what this is, right? Look at the to the right-hand side of this equation. We're taking each observation, x sub I, and we're subtracting it from the mean. And by the way, we're not raising it to the 2 power because we did that with standard deviation. That was the second moment of the distribution. We're raising it to the 3rd power because skewness is the 3rd moment of the distribution. And then to the left of that divided line there, we have to adjust it for not n-1. Remember, I referred to that as degrees of freedom, but notice we have to make some adjustments to degrees of freedom. I tell my students that this is called super degrees of freedom, although that's Jim's term and not any kind of a statistics term. But that gets them some kind of a point of reference to know that we've got to do something other than just n-1. So look down at the bottom 2 arrow points. If skewness is positive, then the distribution is positively skewed, right? And if it's negative, the distribution is negatively skewed. So there's a good answer to interpret skewness LOS. Now, you're thinking to yourself, okay, Jim, there's a first, there's a second, now there's a third moment. Is there a fourth? Of course there's a fourth moment of the distribution. This is called kurtosis. And this has everything to do with how peaked the distribution is. So let me go back here. Notice that normal distribution, that symmetrical distribution there in the middle, that looks pretty much like a perfectly symmetric distribution. Well, and it has an average peak. All right, so let me come here. If we have a higher than average peak, in other words, if that range, and we've done this in blue, is more narrow, we call that leptokurtotic. If it's green, if it's wider, then we call that platykurtotic. And so those are the arrow points there. Distribution that's more peaked, distribution that's less peaked. So leptokurtotic, platykurtotic, and then mesokurtotic. And then the reading cuts off the ot. So leptokurtic, platykurtic, mesokurtic, but I use those other terms as well. Now, notice the normal distribution is neither too peaked nor too flat topped. And so you're thinking to yourself, wait a minute, Jim, let's go ahead and show me that formula. So there it is at the top. And we're doing the same thing, right? We're taking each observation and we're subtracting it from the mean, but we're not raising it to the 2nd power. We're not raising it to the 3rd power. We're raising it to the 4th power because it is the 4th moment of the distribution. And then we need to make another adjustment to degrees of freedom. I tell my students, consider the kurtosis degrees of freedom as the super de-duper degrees of freedom, because I know that many of them watched Barney when they were little kids, and I imagine some of you did too. So regular degrees of freedom, super degrees of freedom, and super de-duper degrees of freedom to visualize those equations for standard deviation, kurtosis, and skewness. Now let's interpret those. Look at the arrow points at the bottom. What we need to do is compute that kurtosis and then subtract 3. So if subtraction results in kurtosis that's positive, we say that's lepto. If it's less than 0, we say that's platy. And then if it equals 0, then we have the normal distribution. And let's finalize this slide deck with what I consider to be a really important LOS. We're going to talk about correlations and covariances throughout level 1 and level 2 and level 3. Let's go ahead and start with covariance. Look at that formula, what we're doing. Now remember, we have 2 variables. So we're taking the observation, every observation for the x variable minus its mean, and then we're going to multiply it by every observation of the y variable minus its mean, right? So we're taking xi minus x bar times yi minus y bar, and we'll divide by the n minus 1, our regular degrees of freedom. There's the sample covariance between 2 variables. And of course, in good financial analysis, there are tons and tons of variables out there that lend themselves to the question, hey, are these 2 variables related? So covariance is a measure of the strength and the magnitude of the relationship between two variables. I mean, maybe we think that changes in GDP are going to have a strong covariance between changes in stock returns. The economy leads to performance on the New York Stock Exchange. Let's go ahead and compute that covariance. But notice here, we don't have to compute it. All we have to do is interpret it. And let me go ahead and pause and give you my kind of a sense of covariance. When you calculate covariance, it can be almost any number. I mean, it could be 1,000,000 on the positive side. It could be 0.45. It could be 0. It could be a minus 0.8. It could be a minus 35. And it could be a minus 2 billion. So I want you to think about this as I'm widening my hands. The term covariance and the statistic covariance can be almost any number. And so how do you interpret a covariance of 6,845,000? I mean, covariance is tough to interpret. That's why really smart men and women have said, let's standardize the covariance into something that's more manageable. So we're going to learn this standardization technique as we move through these slide decks. We take a variable that has a covariance that's this wide. Can you guys even see my hands? And we put it in a vise and we squeeze it all the way down to something that's manageable. And that's all correlation coefficient is. You ready for this? Covariance is a measure of the strength and direction of the relationship between two variables. Correlation has the exact same definition. But since we standardize it, we force that relationship to be linear. And by standardizing, all we're going to do is look at the formula. We've got the covariance in the numerator, and we're going to divide it by the product of the two standard deviations. So that's what we do in economics and in finance and statistics. To standardize a number, we just divide by standard deviation. Since we have two numbers here, we divide by the product of those two standard deviations. And so the squeezing in the vise says something like this. These correlation coefficients have to be either a -1 or +1 or something in between. And so I want you to think about it this way. Here, I always tell my students this, and I go stand in front of the room and I show them these steps because my hands are feet. And so one variable goes like this. If the other variable goes like this, can you guys see that? So whatever one does, the second variable does exactly the same. That's a correlation coefficient of +1. Now, if the variables go like this, if this one moves out this way and this one moves in the opposite direction, but in the same magnitude, and no matter what this one does the opposite, that's a correlation coefficient of a -1. And for those of you who've ever watched Seinfeld, think of that as the George Costanza. There's an episode where George does the opposite of everything that he's done his entire life, and he becomes super successful. But of course, most finance and economic and accounting variables don't have a correlation coefficient that is perfectly -1 or perfectly +1. So I want you to think about this. Suppose this variable goes like this, and this variable goes 75% of the way. And no matter what this one does, this one goes 75% in the same direction. That's a correlation coefficient of 0.75. Now, don't ever tell your stats professors I did this, because it doesn't work on a one-to-one on a daily or a monthly basis. But over time, on average, when one variable goes like this, the other variable will do this 3/4 of that way. And that's a great interpret correlation between two variables. And here's some good pictures here. Strong positive and strong negative correlation if the line that describes the distance between those two variables is pretty close to all the data points. If it's around it, there's weak correlation. And then look on the bottom right, there's no correlation at all. Now here's the great caveat with correlation. I could have one of my sons go outside every day and shoot 10 foul shots and compute the number of made foul shots during the course of a day. Right? That number has to be between 1 and 10. oh, I'm guessing that my children are good enough to make at least one out of those 10 foul shots. So let's suppose that we do this for 100 days, and my son, some days he makes 2 and 8 and 10 and 4 and 6. And I collect data on the delivery time from the Amazon guy because we get a package delivered to us every day. And somehow, the number of foul shots that my son makes exactly coincides with the delivery time. 1 o'clock and 4 o'clock and 7 o'clock coincides with the number of foul shots that my son makes. Well, boy, can we make that conclusion? I mean, how confident would you be if saying, okay, I know exactly when the package is going to arrive at 5 o'clock because my son made 5 foul shots that day. So look at the third one, the third point. Correlation does not imply causation. You've heard this many, many times from your stats professors. So my example there was correlation between 2 variables due to chance relationships. That's probably mine. But when we're talking about things like, what did I say earlier? GDP and stock returns and maybe bond returns and maybe option returns, maybe they're related to a third variable, and that third variable is influencing that high correlation. Let's go back up to the top here. They can have a low correlation despite having a strong nonlinear relationship. So that sounds like a great exam question to me. And then we have to worry about outliers as we have done in other measures. And that takes us through these LOSs. I'm going to go ahead and say focus on LOS 1 and the final LOS. I think those are great ones, measures of central tendency. But then you have to know all of those other LOSs. And then don't forget about correlation. That's super important.